chapter split up over 2 lectures. So I'll come up short this week, I'll just do it next week. But again, I would encourage you to read the book. They're short chapters, but they've actually got a lot of good text in there. You know, so I want to point out some of the important features of this chapter because I want to get you started well. If you got the vocabulary down and the math down and everything down, I think the subject will be clear and easy. But if you don't, then I think the book is frustrating and confusing because you don't understand the words they're using. And so I've kind of divided it up into an introductory portion, and then a little bit on the math, and a little bit, we start into ANOVA, and then next week we'll go into ANOVA more and some more of the examples. So I'm going to do the example in the book, and we'll learn how to really interpret and use the ANOVA function, because that's going to be your main tool in evaluating your results, and we'll try to understand what the book means when it says treatment or sample, or what really clear up the math and the terms, and when they say fixed effects, random effects, those kind of things. What do you mean? What do they mean when they're talking about random error or the treatment error or between or within and those kind of things? Because I think that really helps you understand. So we got chapter 2, and this is lecture 1, and then I'm going to split it up into like I said, intro, and then a little bit on and then on the next thing will kind of be, I'll go down a little bit of the math, and so you'll see what goes into ANOVA and the calculations. And let's see, the intro is going to have a good set of the definition and the objectives. Okay, and then the math, and then if we get far enough, which I think we probably will, we'll begin with the ANOVA. And today will just be how to use it and how to interpret it, and then next week we'll go into a little more details what it means. So that's sort of where we're going. We'll expand this next week in chapter 2 and some more examples. So I'm going to do example 2.1 and 2.2 in the book, and then I expand those next time. And so that's where we're headed. And our objective is to kind of get started with the vernacular and what it is we're doing. So that's it. So chapter 2, if you look at the title, it's single factor, okay, and it's and then they use this other term, complete randomization. So it's good to understand what exactly what we mean, and that's what we're going to get at. So single factor, there's only one thing that we're varying. We're looking at the result of an output versus this one thing. We'll have different levels of that factor, but there's only one knob we're turning. Okay, and then complete randomization I'll define. So and you'll know, like I said, how the chapters grow. We'll add factors, we'll add constraints over here. So sometimes we'll do single factor and other problems because of background variables and stuff, and we'll do multiple factors and then other problems and things. So that's how we'll mix it up. So there's three tenets for this chapter that will allow you to put your design of experiment or your results or analyze your results this way. And that is number 1, that your experimental units. Experimental units. Okay, so these are the things you're sampling, right? Your test people, if you're making a survey, it's your test that you're doing anyway. This is what you're studying, the thing you are studying. However you want to word that. It's a mouse or a person or a manufacturing line. They're homogeneous. Okay, so by that we mean they're essentially all the same. So therefore, this is where we're going to get this word. So this implies that you can randomly assign them to treatments. Okay? And again, these are using the words that they use in the book. So the experimental unit is the thing you're measuring. And and then we're going to randomly assign them to treatments. That's the, the setup we have. So if I'm going to study, this one example they've got in here with houses and different thicknesses of insulation, and I'm going to put it, and I'm going to consider it as a single factor complete randomization, then it's saying that the houses that we're studying and their location and the time and everything else are pretty much the same. Yeah, one might be blue, one might be green, but it doesn't affect the experiment. And that we're going to randomly assign them to treatments if we were varying the thicknesses of the insulation in them, then we're just going to randomly pick this house or that house. Or if it's a person and we're giving them an interview, we're going to randomly assign them to this questionnaire or that questionnaire or whatever it is. We don't have to worry about some of them being in different sets because of the background variables or something like that. So they can be treated all as the same. And so therefore, that's where you get this word. We can randomly assign. We can pick house number A, give it this level of that treatment, house number B, give it that level, or person A and give them that drug, person B, give them the placebo. It doesn't matter. All right, and then let's see. So it's a single factor. That means we've only got one thing to vary. So this implies that our different treatments, if we're going to use their word, are the levels of the factor. Okay, so in the insulation, it would be the 3 inches, 4 inches, 5 inches, 6 inches, those levels. In the drug example, it'd be 0 pills, 1 pill, 2 pills, or no pills, pill A, pill B, or something like that. The different levels that we're doing. Okay, and then so because we're able to do this, the implication is that all of the background variables are either constant or can be made that way. Or essentially constant. So we got time is not a problem, season's not a problem, the people all live in the same area or the same demographics, all the things that would bother us and make us not be able to completely randomly put things in and have to assign them based on some background thing that we cannot control are gone. And we've either controlled them, we've got a nice experimental lab, we've set up the temperature and humidity and everything's fine, or they don't matter, and that sort of thing. So they're constant and similar between all of them. Okay, and so this is what's going to allow us to do this kind of analysis. All right, so now let's see. So now recall that our goal for a design of a statistically designed experiment big goal is to collect our data, acquire data such that we're trying to minimize variation that's attributable and you'll see we're going to do this by controlling sources. So why did I write this here? Because that's the whole thing we're doing in this whole subject. So if we can't control or separate our random variation out, we're never going to be able to make any conclusions. If we're turning up these levels of a treatment changing treatments, changing drug treatments, changing people in surveys, changing things. And if our random variation is greater than our effect, we'll never be able to detect it. We'll never be able to make any conclusions. So the entire goal of this whole subject is to be able to reduce variation that's attributable to randomness, to random factors. So we're going to do that by either controlling the background variables or by blocking and putting our experimental units into groups that have controlled sources of random variation, so that we can say, well, I recognize that this group is different from that group. We can understand that, but then can we look at within the groups or look at the interactions or things like that? So that's why we're going down this path. Now, of course, this is the simplest case where we've got homogeneous units and we're just varying one thing, we're assigning them. So this is when things are really good. And like I said, as the class goes on, we learn how to deal with things that are really bad. And remember, why does it get bad? Well, it may not be your fault. You may be given the data, analyze this, and say, well, how did you take it? Oh, you took it like this, like this, like this. Well, that's okay. All is not lost. We can partition it. Or it may be out of your control even. Your experiments take so long that you can't make time not a variable, or season not a variable, or demographics can't there are things that you can't control for. So at least if you can't control for them, you can partition your data and analyze your data in such a way that you understand that, yes, I have this variation, but it's things that I can explain. So if I can divide up my variation into randomness, things I can explain, blah, 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 and then down here, all that's left is your levels and your treatments, then you can make conclusions about, oh yeah, if I change this, this happens. So that's why we're going down these paths. So that's why we're starting out, like I said, with the single factor, complete randomization, the best situation you could possibly have. All right, so we've got the insulation example, and it's a good one to talk about because it's in the book. Okay, it's on page 11 if you're looking for it. All right, and so let's just make sure we understand what each of the things are, so that we're happy with our words, and when we read the book we know what they're saying. So first, is it single factor? Yeah. There's one of them. There's one single factor. Okay, and the factor is the insulation thickness. So, and I should say a word about what this example is. It's you can look at it in the book, but if you don't have the book, they're studying the energy consumption in a bunch of different houses, and they're concerned. Their question is, does it have something to do with ceiling insulation? So they've got 4, 6, 8, 10, and 12 inches, and they have a bunch of different houses, and they're going to look at the monthly energy consumption, kilowatt hours, I guess. So there's 5 treatments. This will help you understand the words. And the treatments are, the thickness, the levels of the treatment, levels of thickness. We've got 4, 6, 8, 10, and 12 inches. Okay, so one factor is the thickness. There are 5 treatments of that factor, 5 different levels. And then there's 23 experimental units. Okay, these are the houses. Houses. And let's see. And a lot of times the book will count each unit that's in under each treatment, and they'll use a little n to be the count. So if you look at this example, N1 is 5, N2 is 4, N3 is 5, N4 was 6. Oh, sorry, this is 3, wasn't it? Yeah.
No,
3.
that was 5. Next one's 3.
3. Oh, yeah. You're helping me, right?
Right.
That's 5. This is 3.
6.
6. N5 was 6. Yeah. Yeah, I was remembering because it was 10 and 10 and 3, 23. Yeah, so the sum of these is It's the total number of experimental units. And I'm going through this because when we do the ANOVA, and you'll see there'll be, these numbers will appear in the ANOVA table. And those are good things to help you check to make sure you did things correctly. And so if you summed up each of these NI, you get 23. And I hope everybody's comfortable with the, the sum notation. And I guess I should be good, I equal 1 to 5 value. But if I don't put an I equal 1 to whatever, it sums up all of them. But yeah. And so this is the total number of experimental units that's under each level of the treatment. Yeah, okay, let's see. So what else do we want to talk about? Yeah, okay. And measure, yeah, and then our measure or our output measure is kilowatt hours in 1 month. Okay. So now you can see how we're doing. We're not, we're not varying square footage, right? So part of the homogeneity is these houses better be the same size or close to the same size. They darn well better be in the same place, right? It's not going to be fair to have one in Maine and one in Florida. So these are the homogeneous things we have. I'm hoping that, yeah, if we're measuring kilowatt hours, I'm hoping they're heated similarly, right? All of them got electric or whatever, or gas and electric combination. It wouldn't be fair to have one heated with a wood stove and the other one heated with. So that's, you understand what we're saying by homogeneous. We're going to be able to, if we're measuring something and there's a huge factor that affects that, then we better either account for that or get rid of it or whatever. And like I said, maybe you got this data from TVA and all the houses are mixed. And so maybe the way we are doing a single factor complete randomization analysis is we just pick the houses that were all electric and 2,000 approximately square feet in Knoxville. But maybe not. Maybe we've been asked to analyze all these houses. Well, then that's going to be a different technique, right? Because they're different. They're not homogeneous anymore. We can't use single factor complete randomization on ones that are in Maine and Florida and stuff, or ones that are wood stove and gas. But for right now, if we went to all these houses, they'd all look the same. That makes sense. Okay, so now let's see. Yeah, and then the book makes a statement, and I don't think I need to write the statement up, but sometimes I like to, I'll highlight some of these statements so we are aware of them. And the book, in fact, I think I probably wrote it down completely. Page 15, it says, when random error is considerable, it's usually difficult to detect the differences among the treatments unless such differences are even more considerable than the random error. I don't say, well, that, duh, right? But that's going to be our central thing and why we use an ANOVA. So we've got this variation. We've got variation in our results, and the variation, like we said last time, was split up, and that's where the little picture at the start of the, or let's see, not the start, but pretty soon in the chapter, yeah, figure 2.4, shows, figure 2.4 has total variation, okay, and it says, hey, part of it is due to the treatment, okay, and part of it is due to random. And our big question in this chapter is, well, I got some variation, and we know it's made up of these two things. Which one is bigger? Okay? And if this, we know we're going to have random no matter what. I mean, there's no experiment in the world that doesn't have some random error, measurement error, experimental error, those kind of things. And if this is bigger than that, then that means the treatments aren't doing anything. And vice versa. If this is hugely bigger than that, yeah, the treatments are doing something. Okay, well, what have I just said? I've said I want to compare these two. Well, okay, we got to come up with a way to compare them, and a way that's better than just, oh, that looks bigger, or it's we got to come up with something that's defensible and logical, repeatable and understandable. And so, what is that something? Oh, well, it's analysis. Variance. T. I would think that's a good name for it. We're gonna wonder where the variation comes from. Let's analyze it, you know, and this is where the ANOVA part comes from, right? That's the acronym. Those little letters from it, okay? And it's, you know, it's an inferential procedure. You remember from your statistics, that means we're gonna make some inferences. We're gonna make some calculations, some statistically defensible calculation. We're gonna make an inference from it that the inference is gonna be either, yeah, this matters or it doesn't. Or when we get more treatments, treatment A matters, treatment B doesn't, or, oh, well, treatment A and B have a significant interaction, etc. We're gonna infer things from our statistical analysis, okay? And the basis or the theory behind it is that we can partition a variation, okay, and then we can determine, you know, where it came from, the cause. Was it from the treatment? Was it from random? Was it from treatment A, treatment B? Is it from the interaction or whatever? That's what the ANOVA is going to do to us. So now we're standing there. We think we want to do this. We want to make an analysis of variance. We want it to be an inferential procedure. We're going to split up the variation. Oh, this is great. Well, you know, we're going to have some sort of statistic to do that with, right? I mean, we can't just say treatment plots the biggest random. That's good if we're going to be good statistics people. And so we're going to have to choose some statistic if we're statisticians. Now, we don't have to do this because it's already been done for us, right? But if we're going to do it, we have to choose some statistic to evaluate this, whatever this is. And if we choose that statistic, along with that, we got to know, well, what is the distribution? Why is that? Well, remember, you know, before we had all those tests and statistics, you know, sometimes we do a t-test or, you know, a pool t-test, or we do all these things, and each of them had their own distribution, and we'd go calculate some statistic, whatever it was, and we'd compare it to some critical value, like a z-value, or if we didn't like critical values, we'd evaluate a p, you know, a probability, and those. So what it's saying is, if we're going to do this in some defensible way, then, well, okay, we got to make some calculation, a ratio or an absolute value or something, and compare it to some statistic, and then make it, you know, what's the distribution of that statistic, and make some probabilistic conclusion. Okay, well, let's see, what can we do? What statistic can it be? Well, it's going to be this F statistic, and that's why you see the F distribution, and that's what shows up in ANOVA. And so we won't have to deal with that per se, because the ANOVA table is going to spit it out for us. But that's going to be the statistic we use. And I'll visit that again, not on these pages, okay, but anyway, yeah, see. But, and I've got the F distribution anyway, so it's the F statistic and the F distribution. And I think I get to that on these pages, so it must be in the next lecture. I'm trying to do it in the same way the book did. All right, and so one of the things we're going to evaluate for this statistic is very simply, you know, the ratio of the treatment variation to the random. Okay. Yeah, that sounds like a good thing to evaluate, doesn't it? Because if we take the ratio of this variation or variance to that one, and if the ratio is 1, or near 1, you know, less than 1, 1.1, well, that says the treatment and the random are pretty much the same. Not that significant. But hey, as it starts getting bigger than 1, you know, equal to 1, it says, yeah, well, hey, it just looks like it's random. We know that's this treatment and random. Bigger than 1, it means the treatment is important. Oh, okay. That's nice. And so now what we're going to do with the ANOVA and the F distribution is answer the question that we always have to ask, well, how much bigger than 1? And you know, in statistics, when we ask how much, it's always going to be a probability. We're going to wind up with a distribution, and we're going to say, Is it, you know, bigger than 1 at a 10% level or a 5% level or a 1% level? What's the, you know, we're gonna have some distribution, and the F distribution is a skewed distribution, and it's gonna look like this. We'll revisit this. Round 1, and we're gonna come out here, we're gonna get a critical value, and we're gonna say, hey, what's the probability that we would have gotten out here? That's gonna, you know, and if the probability out here is, you know, at 5%, you know, we're doing it at a 5% level, we're gonna say, oh yeah, we got some F, our F from this ratio that we calculated falls out here, you know, F from our experiment. Oh, okay. Well, that's kind of unlikely, wasn't it? That only 5% of them or so fall out there. That means, hey, it's big. Yeah, I'd say treatment matters. But you know, if our F experiment falls down in here or over here, nah, that's not very. You know, that's near to 1. That's almost equal to 1. The treatment didn't matter. It was mostly random. So that's how we're going to decide. Now, the nice thing about you know, remember in statistics we had to go and calculate those with those distributions or do the function in Excel. But when we run ANOVA in Excel, people who've made the ANOVA function in Excel know what you want, and they spit all that out for you. The F comes out, the critical value comes out, the P comes out. So all you have to do is just look at the table and say, oh, okay, look, I'm taking it at a 5% level. Okay, it's important or it's not. And so it's all done for you. That's good. But it's nice to understand where it comes from. So now let's see. So now, knowing that, remember we did all of this, and when you did that in statistics, you did it on the basis of a null hypothesis. And so in our case, in general, most of the situations, not all, but in general, our null hypothesis that we're looking at. Remember, they always denoted that with an H0. It's just that all of the means are equal. What means? Okay, and these are the means from the treatments. Oh yeah, that makes sense, right? Because if I make all these treatments, I change the levels of insulation, and the mean energy consumption is the same. Why is it a mean? Well, because we had 5 houses, we had 6 houses, we had an average, you know, and we had a variation and stuff. So if I make all these insulation changes and the means are all the same, well, okay, then insulation didn't matter, okay? But if it's not the case, if we violate this null hypothesis, then the treatment didn't matter. So in general, our null hypothesis is going to be that all the means are the same from the treatments. In other words, if all the means are the same from the treatments, then the treatment doesn't matter. That's all we're saying. So now, with that basis or that background, knowing that that's what we're going to try to do with our experiments, and the tool is going to be this ANOVA, and that's going to be our statistical tool, and it's related to the F distribution, those kind of things. Let's define what our data table should look like, and get a consistent set of terms, factors, samples, and a consistent set of nomenclature, which is what I'm going to do next, so that I can do a little bit of math for you and just show you what the things that the ANOVA table spits out are, well, how they're calculated, what they mean, just because that helps you, I think. I mean, you can take the ANOVA, you know, once you step back from that, and 2 years from now you want to use it, you can take it and use it and not worry, well, I know how they got calculated. But if you know in the back of your head how it's calculated, what the thing is doing, it's less scary, or you're less afraid to know what the answers are and understand them. So we'll do that much math at least at the front of this book before. You know, we're not going to make it ANOVA. I'm not going to have this program run or anything like that. Although actually, I don't think it'd be very hard. When we think about it, it's just adding up and taking variances and squaring and things like that. It wouldn't be that bad. So if you look at table 2.1 in the book, they've got it's an example of a typical data layout. And I'll write it so we can talk about it. So what you'll have And it's a typical data layout for a one factor too, by the way. Obviously, that's what this chapter is. So what you generally have are the columns, you know, hey, 1, 2, 3, some column, generic column, it's column K. And so this, all of these columns, this is your one factor, right? This is your one factor. And these 1 through K are the treatments. Again, I'm using their words. Their treatments, it's the levels of the factor. Okay. And you can see this in the book. And then down this way are your samples. Running down the columns. So you might have in here a data point, y11. So this is a measure, right? A measure, data point, if you will, whichever word you want to use on that. Can't remember what they use that. So then, y21 all the way down to yn1. Okay, so we're just numbering them. So this is the treatment right here, treatment 1, and then data point 1, 2, 3 down to n1. So like the houses, these are the 5 houses, right, in the first insulation thickness. And then we're just going to number them the same way. My notes are very good. Think about it. Here we would have y1j. So this is how they're numbering things. And this won't matter a whole lot, but it's probably good that you do understand it because they will do the math. They're going to derive it, and if you don't realize what you're doing, you might be you'll hate reading those sections anyway. Okay. I mean, I'm not going to ask you to derive this. 2K. Ah, I can hear things like that without thinking about it, you know. I was at the lab when they had the Y2K stuff, you know. We had the Y2K manager and hours of training and software stuff. Nothing happened, you know. There was a lot of money spent. Y2K, that's good. All right. So we got, so the N sub J here, you know, that's your sample size. Right? So relating it back to the houses, remember that once the 4-inch had 5, and we had the other one that had 4, and the other one had 5, and we had 3. That's how many samples you took under that treatment. And then I made the table look the same, but you might want to try to make N1 and N2 be the same for cleanliness, but they don't have to be. So in general, any old N doesn't have to equal the other. I mean, that's right there in the very first example, insulation, they weren't all the same. So you don't have to have, even though I drew the table that way, these don't have to end with the same number of samples. That's okay, and that's good because your data may not be arranged that way, you know, and so we don't want to restrict that. But if you could control it, perhaps you'd like to have the same number of samples, you know, just trying to get the same, you know, number of data points in each one if you can. That's not bad experimental procedure, but it doesn't matter. All right, so. So if we look at, so using my words again, I keep going back to that insulation example. So our K levels, remember, in the insulation example, just so we can again relate to it, remember there was K equal to 5 because there were 4-inch, 6-inch, 8-inch, 10-inch, 12. So K equal to 5 in that example. Had 23 data points in here. And let's see. So for example, you know, the third level, that was the 8 inches, trying to make sure, yeah. Yeah. So now, let's examine some general data point. You know, maybe the I-J data point. You know, row I, come over here. So let's look in here at Y-I-J, a general data point, and let's talk about it and talk about what is it made up of mathematically, so we can look at it and relate its value to the values that show up in the ANOVA table. We got this data table, we've arranged things nicely, we've done our experiments, we go with one data set. Out of the middle of the table, one random data point. So if we looked at some random data point, what did I call it? Yeah, just one sample, right? Randomly picking sample I-J, all right? And it's going to be made up of three primary things right now. It's made up of the mean, right? And some mean over everything, some giant mean. Okay, it's going to be made up of something that had to do with the treatment, right? I'll spell ways out. Okay, and then it's also going to have a random error. Okay, so let's think about it, right? So this here, okay, this would be the mean over all of the data. Okay. And then tau j, that's going to be the effect on this one data point, Yij, due to the j treatment. Correct? Because data point Ij that I raised was in the jth column, the ith row, and the I is just a counter for the sample. One house, two house, three house, four house that had 8 inches of insulation. And then the epsilon Ij, okay, that's the random error. For the I sample. So I hope you can understand why it's subscripted the way it is, right? If we have this giant heap of data, and the house is a great example, we have this giant heap of data that we've taken, and it's got two major effects in it. One effect is the treatment, the insulation thickness. The other effect is randomness, right? So any general data point is going to have the meaning of all the data in it, obviously, and it's going to vary from the mean. It's going to vary due to the treatment, and it's going to vary randomly. Well, the variation due to the treatment is only subscripted with J, right? Because everybody in the jth column had the same treatment. They all had 8 inches of insulation. It doesn't vary with I, right? All the samples in there had the same treatment. But the random error will. It's going to vary for every different sample, because each different sample is another experiment, another day, another person, another instrument. So it's going to have both the sample variation and the treatment variation. So, well, this is great. We've now realized that each data point has got some large mean on it, and this and this. Okay, so now if we can understand these relative differences, that's good. We can make a decision. The treatment mattered. Now, we don't want to just look at each data point, though, right? We want to make an aggregate. We want to look at, all the data points and the treatments, all the different samples and all the treatments to make this decision. So we can't just, take the ratio of that to that. And besides, if we just have one data point, how in the world do we know? If I take one data point and it's some number 12, well, was it 6 and 3 and 3? Well, 7. And, we could go on all day. So we have to have many data points, and we have to do some sort of analysis to flesh out this and that, and then ask ourselves what the relative difference is. All right, so let's think about that. And then I'll make this comment here, and I think it becomes more clear as we go through the work, and as we as we study it, but the book, maybe I shouldn't do it here. The book does. The book introduces this notation, then they make a note, they go on a little tangent about fixed effects versus random effects, and when you read it, you're like, wait a minute, what's going on? I'll put it in here and we'll revisit it, but at least you'll know. And I did a little internet research on to see what other people being people in different disciplines, how they distinguish fixed effects and random effects. And there was a lot of discussion. But the simplest things, so if you have a fixed effects model, we'll like I said, I'll revisit this because I don't think it's clear from this. There are just a particular set of levels. Okay, and if you had what's called a random effects, and I think, I bring these things up sometimes because you probably this whole class and not distinguish the difference. Yeah? Is the orange too hard to see? Yeah. I should only use the orange then rarely, right?
Well, if they got the lights on, they'll see it.
Yeah. How's that? Or should I get the black?
Black may be a test.
Yeah. And restricted colors just to expounding on things, yeah. Oh, perfect. I've got a yellow one in my backpack. That's even better. That's one of those ones too that got the smell to it. So I sit up here. So again, we said there were particular levels. And I'll expound on that. And then there's random things. Yes. Your levels. So, what does this mean? All it means is the fixed effects. You have fixed particular levels and no more. So the insulation example, we had 4, 6, 8, 10, and 12. That's it. There weren't any others. Random effects is we had a zillion different levels and we randomly picked some to study. So maybe if we had 50 different insulation thicknesses, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 30 inches, and we say, well, I can't study all of them, let me randomly pick 4, 6, 8, 10, and 12. That would be a random effects analysis. But in our experiment, we just had 5 levels. It's a fixed effect experiment. And in general, so one source I read on the internet that said, oh, fixed effects means you checked every level that was possible. And random means you had to select some. Okay, that was one distinguishing thing. And then your book pointed out that, well, in general, a quantitative experiment would probably have fixed levels, whereas a qualitative one might have random because you might have too many things to pick from, like demographics or something. Yeah, fixed levels, exhaustive population, random, they're samples. Yeah, and what's going to matter, it'll matter a little bit in how they treat them statistically, but it won't matter for right now. Because right now we're going to launch into, the first example, the math we do is a fixed effect. Okay, so just so you got those two definitions and consider that a tangent, and now we'll come back. And again, why did I do that tangent there? Because your book does. And if you're reading along in the book and you get to the section with the y equal to the mu and the tau and the epsilon, then you say, wait a minute, what's this page and a half of crazy discussion? Well, that's what it is. All right, so now let's see. So back off of that tangent. I was like, you got to identify a tangent so you know. So if you're going through your notes, you do like I used to put a big circle around that and say, okay, weird tangent. Don't worry, it interrupts the flow of things, and it goes in the book. All right, so let's see. So what we're gonna do next, and our next objective is, math. But our next objective, and this will help you so you don't just say, what is he doing? So our next objective is, we're gonna look at the variation. We're gonna try how to make this nice. And we're gonna understand, not just making this up right now. So we're gonna understand how to partition the variation. And this is gonna involve some math. And then we're gonna relate this, and then we're gonna just show this here's, you know, all right. So that's our objective. So to achieve this objective, I'm gonna have to study the variation in that nice little data point we had, based on relating it to the other data points and the means and the averages of the treatments and the overall mean, and kind of form some differences, form some variances, calculate them, and take this ratio, and then arrange them in a nice little output, and call that an ANOVA. So to achieve this objective, we got a page or so of a few calculations. They weren't very hard, but will help you understand what goes into it. So let's go back. And so remember, we had this general data point. Just remember that's the data. This is just one. I shouldn't call it data point. Let's call it one sample. This is the grand. Back in your old statistics, that was the grand mean. This is the treatment. This is random. So now, so this is the variation among the groups. Maybe this is within. That's a term you'll hear. So let's start playing a little math. And most of the math we'll do is just some algebra and simple things. So first, let's just subtract the average from both sides. Okay. And again, I'm doing this because I want to explore what these are, the ratio of these, and come up with a way to examine this ratio and compare it to the F distribution and make a decision on whether the treatment mattered or not. All to distinguish that from that is all we're doing. Okay, so now let's introduce some new notation. And I'll just plop it out here and then we'll talk about it, right? So what is this new notation? And then I'll define them, I guess is the way to do it, perhaps. Let's say, oh goodness, I've never seen this. Okay. Talk about it again. Probably shouldn't put an intermediate step in here in the notes, but maybe it's okay. Because maybe with words, if everybody likes it, we'll do it with words, and if not, I'll introduce the new notation, then I'll define it. This is equation 2.6. Book 2 if you're looking around. Okay. And so let's define what these terms are, so that we don't think, good Lord. So the first thing is, when you introduce these dots, it means you summed over that index. So let's look at this first one, because I think it's the easiest one. So this Y double dot means that I summed up double sum. NJ, J equals 1 to K. Right? K was the number of treatments, NJ was the number of samples under each treatment, 5, 3, 5, 4, those things. This was 5, there were 5 treatments on the insulation. So I just added up all the data points, right? And so, yeah, hey, good, I was thinking that I made a mistake there. Subtle difference, but okay. Now what does the bar mean? Well, it means you just made it a mean, right? Big giant, you know, to find that of the double sum of y by j. Where the big giant n is the sum of all the total data points, right? So in this case, the big giant n was 23 in the insulation example. So what this is just another way to write the mean. And I'm writing it by saying I'm summing completely over I, completely over j, and dividing by the total number. So you can now guess what this one is, right? That one would be, without the bar, y dot j is the sum from I equal 1 to nj of all the data points. Okay, and then y dot j with the bar is 1 over nj of that sum. So in words, what are they, right? Well, so this one is the big mean, right? That's the grand mean. That's the mean of all of the data points in the whole table. This one is the mean of just the ones in the one column, just the ones in the jth treatment. And so what have I written? And then if you look at this mathematically, yeah, I've rewritten the mean, and what I'm saying here is mathematically, I think once you see what we use the words, you're going to say, well, duh. I'm saying that the variation due to the treatment is just the difference in the treatment mean from the whole big mean. Well, yeah, that makes sense, right? I just took the average of all the guys in one treatment and compared it to the overall mean of the entire data set. Yeah, let's say that's what the treatment did. Okay. And then what am I saying the random error is? The random error here, E, is just how much each tiny data point varies from its own mean in the treatment. Yeah, that makes sense. Go down through all I, compare each, for a given J, for a given treatment.